Building a database to track high-resolution personal habits is a standard engineering exercise. Building a database to generate macro-level economic reporting requires massive aggregation. Attempting to do both within a single architectural space creates an immediate structural paradox. Project NEXUS, specifically its version 1.5.0 release, offers a definitive case study in solving this exact micro-to-macro data engineering challenge. On the micro side, the system is designed to capture highly subjective, granular user interactions. It logs individual milestones, assigns community mentors to specific goals, and records routine emotional check-ins from individual members. On the macro side, the architecture must instantly ingest those subjective personal feelings and programmatically aggregate them into a strict quantitative social return on investment metric for platform administrators. When developers try to satisfy both requirements, they usually fall into one of two traps. They either duplicate the data across multiple synchronized databases, or they construct sprawling graph webs that become entirely unqueryable at scale. The NEXUS solution abandons those workarounds. It relies entirely on a strictly normalized, unified relational schema that functions as a dual-purpose engine, serving the user and the administrator simultaneously. Mastering this specific architectural balance is the dividing line between building simple CRUD applications and engineering enterprise-grade impact systems. This entity relationship diagram displays the foundational goals table schema. Notice the isolation of the current value float, the target value, and the status column. This is where state management begins. Instead of importing external state machine libraries to manage a goal's lifecycle, the system enforces strict database enum constraints. A goal can only ever exist as active, completed, achieved, or abandoned. When a user clicks a button to update their progress, they are simply triggering an API endpoint that increments that current value numeric float. The backend intercepts this increment request and executes a basic comparative algorithm against the target value. If the current value equals or exceeds the target, the system takes over. It forcibly updates the enum status to completed and immediately executes a webhook, awarding the user experience points for their progress. We see a similar constraint applied to human emotion. This diagram of the goal check-ins table schema highlights how highly qualitative user reflections are sanitized for the database, specifically expanding the mood column. A user's subjective emotional state is stripped of free text variants. The database restricts their input to one of 6 exact enumerations: great, good, okay, struggling, motivated, or grateful. This restriction guarantees that qualitative human feelings are converted into indexable data rows. By enforcing these enumerations at the point of entry, the system bypasses the high compute costs and error margins of post-processing unstructured text, allowing the macro engine to perform real-time aggregation. Scaling up from flat personal goals, we encounter the Deliverables ecosystem, where multi-user project management demands a massive structural leap. True project management requires deep nesting, tasks within milestones. Typically, avoiding severe query latency in these structures requires migrating to a dedicated graph database. NEXUS bypasses the graph requirement entirely. This graphic maps the flattened 30-column deliverables table, showing a self-looping connection line that routes the parent deliverable ID column directly back to the primary ID column. By utilizing this self-referential foreign key, the single table generates a relational tree structure. This allows subtasks and milestones to link to parent tasks through multiple levels of recursion. Because of this single column, the front-end user interface can render the entire hierarchy using a simple has-many-children relationship, entirely avoiding heavy recursive loops on the back-end. Governing a deeply nested multi-user hierarchy requires absolute accountability regarding who changed what and when. To maintain integrity, a secondary deliverable history table acts as a continuous audit trail, monitoring exactly 14 distinct action types across the entire tree structure. Every time a priority shifts or a deadline moves, the system irreversibly logs the before and after values, the executor's IP address, and their specific user agent. This self-referential design provides the recursive depth of a graph database, while retaining the row-by-row auditability of a traditional relational schema. The final architectural hurdle in the meso layer is resolving horizontal blocking logic and cross-referencing dependencies between entirely unrelated parent tasks. Vertical parent-child nesting is straightforward, but parallel project management requires that a task in one department can halt the progress of an unrelated deliverable. Look at these two parallel rows in the deliverables table. NEXUS stores cross-referencing logic directly inside the primary table by isolating the blocking deliverable IDs and depends on deliverable IDs columns as raw JSON arrays. This is a strict read optimization strategy. Storing dependencies as JSON arrays means the interface can parse all blocking requirements in a single query payload, avoiding expensive recursive database joins just to disable a complete button. The risk here is data integrity. If a blocking task is deleted, the ID stored in the JSON array becomes orphaned. The application layer must step in to strictly enforce cleanup. The system operates on dual mechanisms. Standard database cascading deletes manage the vertical parent-child structure, while raw JSON arrays manage the horizontal lateral blocking. Combining relational foreign keys for depth with embedded arrays for lateral cross-referencing creates a frictionless dependency engine that remains highly performant at scale. This micro-level infrastructure exists to serve the macro layer, taking thousands of completed tasks and check-ins and converting them into quantifiable economic impact. The central mathematical question of the architecture is how an individual user's click transforms into a verifiable social value dollar amount. The social return on investment metric used here is a deterministic algorithm anchored to database timestamps. This formula illustrates the exact programmatic pipeline. Step 1 sweeps the deliverables table, aggregating the transactional amounts of all completed tasks into raw hours. Step 2 multiplies those total hours by a tenant configurable baseline, defaulting to $15 an hour, establishing the raw monetary value. Step 3 takes that monetary value and scales it by the platform's standard 3.5x social multiplier. This derives the final social value. The ultimate output is generated by calculating the calculated social value by the base monetary value, producing the final SROI ratio displayed to administrators. Simultaneously, this macro engine sweeps the user tables, cross-referencing active traders against the total population to generate precise community health metrics, like network density and reciprocity scores. The resulting economic math carries weight, precisely because it is extracted from a rigid, queryable pipeline built directly on top of the micro-layer's strict enumerations. This service map diagram visualizes the complete dual-purpose ecosystem at scale. 10 dedicated backend services, routing through 30 RESTful endpoints, all converging on a single unified database. Modules like the Goal Service and Impact Reporting Service sit precisely between the raw relational tables and the front-end interfaces, orchestrating the flow of data. The API functions as the absolute gatekeeper. It silently enforces privacy constraints, checking booleans like is public, ensuring private user goals never contaminate the public aggregate SROI queries. Complex software ecosystems do not require disparate, fragmented microdatabases to serve distinct audiences. They require tightly indexed, unified schemas governed by strict programmatic logic. The NEXUS model demonstrates that translating local user utility into quantifiable global system value does not require a fragmented infrastructure. It requires a single, well-governed source of truth.